let's take a little while to look at some examples of factoring, especially the kinds that involve squares. So we can take the difference of two squares and factor it. We can factor some things into a perfect square, and we can use that to then complete the square if it doesn't fit the right form. This first example has two terms and it's a difference. So it makes me think it probably has something to do with the difference of two squares. So if you remember, the difference of two squares means that if we're subtracting two things that are perfect squares, we can factor it into x minus a times x plus a. So this is the form we want to find and then use to factor these types of equations. So this first expression that we have here, it doesn't quite look like it fits this form, right? The 36 is okay, that's just 6 squared, so it makes me think that a is probably 6. But then we have this x to the 4th out in the front term. That's not the same as x squared. However, we can write x to the 4th as x squared times itself, which means that x squared squared is the same thing as x to the 4th. So now my x is x squared, my a is 6. We do have this written as the difference of two perfect squares. So we end up with x squared minus 6 times x squared plus 6. Now x squared plus 6 doesn't look anything like the difference of two squares, seeing as it's not even a difference. However, this one does still kind of look like the difference of two squares. But 6 isn't usually a number we think of as a perfect square. X squared is, 6 isn't. But anytime we have a positive number, we can always think of it as the square root of itself squared. So we can rewrite 6 as the square root of 6 squared. So now we do have the difference of 2 squared. X is just x, and a is the square root of 6. So we can then take the difference of 2 squared again to factor this further. And now we can call it quits. We have three terms, three factors here now. And we've been able to factor this equation once by using the difference of two squares, and then again by using the difference of two squares. So that's how we were able to get three factors. Okay, this second example has three terms, so it's definitely not the difference of two squares. So if anything, I'm hoping that this will be something we can factor into a perfect square, something like x plus a. So the form for that was that x plus a squared is equal to x squared plus 2ax plus a squared. Okay. So we need to determine if this is the form that this is in, we can then factor it to be x plus a squared. So if this is the right form, then my middle term is 2ax. Well, then that means that my 2a is equal to 18. So 18 is 2 times 9. So that means that I'm thinking my a is going to be 9. Well, if indeed this term is 2ax and this term then is a squared would be 9 squared, which is 81. So we have the form we want. We have x squared plus 2ax plus a squared, where a is 9. So I can factor this to be x plus 9 squared. So this is why knowing this form is helpful for examples like this. Now this third example also has three terms, and it looks like it could potentially be in that same form. So 2ax in this case is negative 8x. So 2a is negative 8, so a must be negative 4, because that's what 2 times a being negative 8 would imply. So, what's negative 4 squared? Well, that's the same thing as positive 4 squared, or 16. So indeed, we get 2ax here, and if a is then negative 4, this is the same thing as a squared. So, if a is negative 4, what we end up with is x minus 4 squared. We were able to factor this trinomial or 3-term expression into x minus 4 squared without too much difficulty even. Once we found what a should be, we found that it worked with a squared being the 3rd term, we were able to factor it. Now let's look at this 4th example. We're back to only having 2 terms, so we're probably looking at something similar to this, if we can factor it at all. And again, negative 1 or minus 1 is the same thing as minus 1 squared, so I'm seeing minus a squared where a is 1. That's okay. It's this 5x squared that's bothering me. But remember what we did with the 6? We changed it to not be 6, but square root of 6 squared. That's what I want to do here. Move this out of the way so we don't get confused. We have the square root of 5 squared times x squared minus 1. Well, if I'm multiplying the square root of 5 squared times x squared, that's the same thing as taking the square root of 5 times x and squaring it. Because I can multiply in whatever order I want. So here my x is the square root of 5 times x. My a is 1. So I end up with the square root of 5 times x minus 1 times the square root of 5 times x plus 1. X minus a times x plus a. So this was another example of the difference of 2 squares. Now let's look at this last one. It looks to me, especially because it has 3 terms, and the numbers look like they might fit, like it could be close to this form, except that I have x to the 4th and x squared instead of x squared and x. Well, let's think back to what we did when we saw an x to the 4th here. We rewrote it as x squared squared. So I can rewrite this as x squared squared minus 4 times x squared plus 4. So what I'm seeing here is that I have this same form. I have something squared times 2a times something plus a squared, if a is negative 2, right? Because 2 times negative 2 would give me negative 4. And then negative 2 squared would be positive 4. Except that my something, my x from here, is the same thing as x squared in this case. So I can factor this to be x squared minus 2 all squared. Or if it helps you, you can use the substitution y equals x squared, and then you end up with y squared, because that's going to be just y now, minus 4y plus 4. Then it'll be easier to see that you have exactly this form with a equals negative 2. You end up with y minus 2 squared. But we started with x's, and if I had forgotten to write that down, I'd probably understand what this meant and how I got there. But no one else would, so we need to put that x squared back in there. Now we could go ahead and actually do the difference of 2 squares here, right? So we have x squared minus 2. Well, we can rewrite 2 as the square root of 2 squared. So we have x minus the square root of 2 times x plus the square root of 2. And I'm squaring that whole entire thing since I was squaring all of this. So that's the same as taking x minus the square root of 2 squared times x plus the square root of 2 squared. If I multiply this times this times this times this, it's the same thing as multiplying this twice times this twice. So this is what we end up with when we factor this. Notice that this one has 4 factors, 2 here and 2 here. Okay. So all of these have worked nicely, but that's not always going to be the case. There's a lot of functions that we can't, or expressions that we actually can't factor using either of these two methods. Like, let's look at the example x squared minus 4x plus 7. So if I look at this form and I want to make it fit so I can factor it, 2ax is negative 4x. So 2a is negative 4. That means that, again, a would probably be negative 2. It's the only thing that makes sense for a. But then if I take a squared would be 4, not 7. So this is not the same form. So I can't just factor it to be x plus negative 2 squared, x plus a squared. It doesn't work. But what I can do is I can force kind of a perfect square to show up in here so that I can factor this, and then I'll have a little bit left over at the end. So I can do that by taking this and using the fact that I know that if this were a perfect square, a would be negative 2. So I take x squared minus 4x, and then I want a squared to show up in there. But if I add that in, I can't just add that in without changing anything, so I need to subtract it off again. And then that plus 7 needs to come on down with it. So now this, I just made that look like this. I just did that on purpose. I found a from my middle term, and then I squared that a. So I purposefully made those first three terms look like my perfect square. So this would be x minus 2 squared. Then I have negative 2 squared is 4. And then plus 7, just came along at the end. And then I can combine these two like terms. So I have x minus 2 squared minus 4 plus 7 turns into just plus 3. So again, this isn't as handy as if I had actually factored it, because I can't use the factors just as the roots of the equation, because this plus 3 is hanging on at the end. But it still can help us solve for x if we were to try and do that. Let's do just one more example of completing the square. So let's take x squared plus 5x minus 3. So if I'm trying to figure out whether this is in my perfect square form, 2ax is equal to 5x. Now I don't know a whole number that multiplies by, or that when I multiply it by 2 I get 5. Right? 5 is not an even number, so I can't divide a 2 out of it evenly. So if 5 is equal to 2a, well that means a is going to be equal to 5 halves, which is the same thing as if we were to talk about 2 1/2. But we're going to keep things in not in mixed numbers, in fractions, so that it's easier to square. We'll see that as we keep going it'll be easier. So if this were to be a perfect square in that form, this minus 3 would have to be 5 halves squared. Well, 5 halves squared is always going to be positive. So I know right off the bat that negative 3 is not a squared. So what I need to do is I need to do exactly what I did here. I'm going to add in a squared, subtract it away, and then I can factor inside. So I'm going to add in a squared, subtract off, because I can't just add it or else I'll change my equation. And then that negative 3 just kind of comes down along with it. So I just forced these three guys to be in this form. So I get x plus 5 halves all squared. And then I need to square this 5 halves. So 5 squared is 25. 2 squared is 4. So I square the top, square the bottom. And then I have a minus 3. But I actually want to take that not as minus 3, but I want to multiply this by 4 over 4. So 3 times 4 gives me 12, and then 1, because 3 is just 3 over 1, times 4 is 4. So now I have common denominator, so I can actually subtract these. So minus 25 minus 12 all over 4 is going to be minus 37 over 4. So that would be how we would complete the square in this